Hello, everyone. Welcome to our talk, The Hole in Sandbox, Escape Modern Web-Based App Sandbox from Set Isolation Perspective. I'm Bohan Liu. This is my partner, Haibin Shi. We are all security researchers at Tencent Security Xuanwu Lab. I'm mainly engaged in browser security and also a Google Chrome bug hunter. Haibin focused on Android security more, so this is a talk combining browser security and Android security. Let's start this talk from the part of background and knowledge. As shown in the picture, the Chrome is a multi-process browser. We can see that when a page is opened, each process has different work to do and gently renders the page. For example, the browser process controls the interactive parts visible to the user, such as address bar, back and forward button, and also invisible parts such as network requests and file access. The render process controls anything inside the tab where a website is displayed. Any code related to the page rendered here, including JavaScript, HTML, CSS, and so on. As we can see, all code about the website was loaded in rendered page. So if any bug here, attacker can get all permissions of render process. Therefore, Chrome uses a sandbox to limit render functions, so attackers can't do much things. The first main idea is do not reinvent the view. Therefore, the sandbox reuses the system restrictions to grant low-power permissions to the render process. For example, the integrity levels was used on Windows, seccomp BPF on Linux, and SE Linux on Android. This makes Sandbox meet the principle of least privilege, and the render process only can access limited resource and IPC or kernel interaction. So what can a hacker do after getting the render RCE? First, they can access the limited system call, for example, calling mprotect to unlock memory with any permissions. But they can't do really dangerous things like downloading any files, creating process. In this situation, hackers may violate their permissions via system bugs in the limited system call. Second, they can send IPC calls with evil parameters. If there are any bugs in browser process and when handling IPC, attacker will eliminate with their permissions by getting RCE in browser process. The above are popular ways to sandbox escape at present. Of course, they all required another bug. Another capability is patching all code and data in render process. There is a special sandbox escape case from Black Hat USA 2022. Attacker can call any native Node.js APIs by modifying some data related to the iframe. Via these APIs, attacker can escape sandbox of Electron applications. What is the greatest capability of render RC itself? Can it only be used as the precondition for a sandbox escape? This is also the original intention of this talk. We hope to explore how to push the render RC itself to its limits. According to the Chrome vulnerability reward program rules, there are some other high-risk bugs between sandbox escape and the render RC here. So can we increase the risk level of render RC itself step by step and finally achieve sandbox escape? There may be two ways to choose here. First is GPU or network process RCE, which is a process with medium permissions. But those process RCE also requires privilege escapation bug. So can we try universal cross-site scripting first? So let's come to the part 2 with this problem. I think everyone here may be very familiar with cross-site scripting, also known as XSS. But what is universal XSS? This is a simple picture to show the differences between them. When there is a bug in the server code of victim.com here, the attacker tricks the user to load a link containing evil parameters. After that, the XSS payload is injected into the page on the server side. When the page is loaded in the browser, any JavaScript code will be executed in victim.com, and the attacker can steal the user's cookies. As for universal XSS, the bugs is in browser. When universal XSS payload is loaded in the victim's browser, attacker will use the bug to inject JavaScript code into victim.com even if the server side has no bug. The cookies can still be stolen. After analyzing the historical data, this type of vulnerability began to exist as early as 2006. From the figure below, we can see that from 2010 and 2024, IE, Safari, Firefox, and Chrome all had such vulnerabilities. In particular, 63 vulnerability universal access bugs appeared in Chrome alone between 2014 and 2016. So universal XSS is a kind of high-risk vulnerabilities that has existed for a long time and affected many browsers. So what stopped us injecting code from other domains? We can do a small experiment. We know that the DOM tree contains all the code of a page. We can visit it by the object document. First, we create a new iframe and set it a different domain from the parent page, such as xlab.tunson.com. When trying to read and write its DOM tree from the parent page, we found it was blocked by the SOP of browser. The same origin policy, also known as SOP, is a critical security mechanism that restricts how a document can interact with a cross-origin resource. It checks whether the triples of parent page and child page are the same. The triples are applicable, domain name, and port. In our case, the domain of iframe is different from the parent page, so the access is blocked. Now, the question is how to bypass SOP. Here is a case worth learning, telling us how to use a render RCE to bypass the SOP in Safari. It comes from a topic of Blue Hat 2020. The attacker can use an iframe to load google.com in the attacker.com and then exploit a render RCE bug in parent page to inject a B-tree JavaScript code into google.com. There are three conditions of this attack path. The first is the attacker's page and the victim iframe are in the same render process. And second is that the SOP check is in render process rather than in browser process. The third is that domain structure used by this check is also in render process. So attacker can modify data in render process to bypass the SOP. Specifically, the attacker can overwrite M universal access of domain to bypass check of cross-domain data access, so the attacker can inject any JavaScript code into iframe page. Of course, X-frame options will block set to be loaded in an iframe. However, this check is also in the render process, so attacker can bypass this check again using the same method and make any site loaded in iframe. So comparing those 2 points, attacker implied universal XSS in Safari. It sounds like good news, since Chrome and Safari used to share the same render engine that was WebKit. So this attack method in Safari may affect Chrome as well. However, Chrome designed a series of universal XSS hardened to defend against them. First, Chrome introduces out-of-process iframes. It allows a child frame of a page to be rendered by a different process rather than its parent process. So it killed condition 1. Second, Chrome introduced the PLZ navigate. It moves cross-origin security checks to browser process, so it kills condition 2 and 3. What's more, Chrome introduces set isolation on 2018. It limits its render process to load a single site. It is called the most promising countermeasure against universal XSS attacks. Set isolation seems a problem we have to face, so let's come to the set isolation now. Its principle is treating each website as a separate security principle requiring a dedicated render process. So there are mainly 5 new features added in set isolation according to the paper. Among them, set principles and dedicated processes are concepts used to define the implementation method of set isolation. Well, cross-process navigation and out-of-process iframes are the scenarios in which set isolation is added. In out-of-process iframe scenario, when the parent page contains a cross-origin iframe or pop-up page, they are loaded in a new process. In cross-process navigation scenario, when the navigation target is cross-origin, it will be loaded in a new process too. Now, we understand the principle of set isolation. Let's take a look at its implementation. We can find it in start navigation method. We know that a render frame host represents a render in the browser process. So during navigation, the render which the new page is loaded will be determined based on the associated RFH type marked in red here. It's determined by use current RFH in getFrameHostFromNavigation, and this is determined whether the current site instance and is constant with destination site instance. Finally, we found that the generation process of destination site instance will try to reuse the origin site instance. If possible, it will be loaded in the old render frame host. Otherwise, it will be loaded in a new one, which means a new process created. The key to decide whether to reuse process is in use dedicated process for all sets method. For example, when the strict set isolation mode is not met, the new page will be loaded in the original process with navigation. So what is strict mode? We can know it from the doc. The strict mode is only for desktop platforms, so the process will be reused in the partition mode, such as Chrome for Android, and this set isolation will also occur in all Android platforms, such as WebView. That's it to say, we can reuse the same process after navigation in Android. Now, hackers have the ability to patch all code and data based on the render RCE, and the following page can be in the same process attacker controlled. The next step is to find a way to inject JavaScript code into another page. There are many times to choose from the perspective of page rendering. I chose the JavaScript compilation fast. The JavaScript code here is a string at this time point. So what we need to do is finding and modifying them. I found the compile script internal method, the compilation function in Chrome. First, it takes out the JavaScript code and generates a V8 string object here. And then call compile method of script compiler. This is a good point to hook. So I hook this call point into an evil V8 string. This looks like a Trojan horse. When certain conditions are met, evil V8 string modifies the JavaScript code into our payload, like alert pound. Otherwise, it compiles normally to avoiding strange behaviors. So the whole attack process is like this. First, victim opens the attacker's website, and then attacker patches the code via render RCE. It injects a Trojan horse into compile script internal, and then navigates to the victim side by reciting the location.href. When compiling this JavaScript of victim page, the Trojan horse triggered and modified the JavaScript as anything controlled by the attacker, causing the universal XSS. Okay, we take a step forward. We transferred the render RCE into a universal XSS. I make a demo on Chrome for Android 90. On this version, we can inject any code into some important sites, such as account.google.com. Let me play the video. Okay, we can use Chrome 90. Okay, we can, the pond was shown on account.google.com. After I talked about this method with Gongguang on TFCup, he said he is similar to his another bug used on PwnFest 2016. This is very coincidence, so I also list his method here. After I submit this issue to Google, however, Google said it won't fix since they can't do anything. They can't do much thing until they enable strict site isolation on Android. But as users, they are still be safe since Google uses heuristics to isolate the sites that need isolation most from Chrome 92. This means we can't inject JavaScript code into sites that like account.google.com after that. So what are the sites that need isolation most? According to the Google's doc, it mainly protects private data related to the user login, such as the sites that users log in by entering the password, or sites with the industry standard or else protocol. Since that, what other unprotected but equally dangerous sites are there? From the perspective of Android Chrome developers, just protecting those sites is enough, but there is a category of apps called web-based app, implemented by browser components using Chrome. Usually, web-based app has more complex functions. Could those apps survive under this attack using similar protection? Okay, this is another question. So let me give the lifetime to Haibin. He will introduce how we escape the sandbox of web-based app using this method. Okay, welcome, Haibin.
Hello, I'm Haibin. I'm going to show you how we escape the sandbox in real-world software. First, let's analyze the web-based app from site isolation perspective. Web-based app use a web view or other similar component like CEF to show web content. These components are often based Chrome. Such powerful component may cause more problems than native application. Oh, sorry. Sometimes developers not only want web content display, but also interactive with their local resource. Therefore, web component also come with JavaScript interface, which can give JavaScript ability to call native code. Some JavaScript interface actually implement very powerful function, such as install and open application. If we can call this interface, it's possible to achieve effect of sandbox escape. But developers also come up with this and limit use of privileged application interface to only websites they trust. The following is a code example. Like this. Before call privileged application interface, there is a domain check. It seems very secure. is it possible to break security exception in a perfect site isolation? There is indeed no way to do that. However, after our research, we found that due to the implementation of site isolation, there are security issues in many web-based apps. Many apps don't implement full site isolation. We may use universal XSS solution to call any privileged application interface to achieve effect of sandbox escape. Now let's show how to escape modern web-based app sandbox from site isolation perspective. Here are some software we care. For example, PC application-based CEF, default mobile browser, application store, and so on. The first type is the PC application-based CEF. This is a web-based app architecture with the following two features. First, privileged application interface mainly implement the common function of the client. Second, many implicit deep links are registered in privileged domain resolution. For developers, the most important thing is the running speed of the software, so there will be many optimization, especially regarding the process of loading page. A case is the render process created when the app open and reused when website closed. It kills the site isolation when only one tab used. Hacker can get universal XSS in privileged domain using a render ICE bug. And then we find bugs in privileged application interface. First, we found two bugs in crypto application interface. We use Windows UNC to control the input file as a remote file. We can also get path traverser when writing files, so we can write any value to any file. And we found another interface which can start a process with a hardcode name. Choose them, we got RCE. There is an exploit demo video. What we are going to introduce next is the mobile browser. Default browser or mobile phone is pre-installed, so it is the attack entry point for Pontoon's mobile project, which may imply one-click RCE. It's an attractive target for security researcher. Each brand mobile phone will pre-install their customer browser. Only Google Pixel 4 carry Android Chrome. Mobile vendor customer browser open secondary development-based Android Chrome, which are potential site isolation too. So we can achieve universal XSS in this target too. Then we need to find some some useful JavaScript interface. There is a case. There are some advertising functions in target app, which enable silent app install and open. And after analyze, we found that such powerful functions are implemented by JavaScript interface. But these high-risk function can only be called from privileged domain. The following is the target interface. The first is the browser.openApp. App can be opened based on the app name string. Another is browser.installApp. App can be installed based on the app name string, and a callback for install app can be set. We can use this callback to open app after install. But this is not good enough. We found that only apps in the App Store can be installed. That means we need to upload self-developed app with a backdoor to App Store, just like most of the Ponto players in recent years. However, this method takes more time and carries the risk of being discovered by auditors. But we have to rush to participate into Tianfu Cup. And there are other ways to exploit. After analyze, we find a possible solution. We should control the device through app already in App Store, and the target app need to be able to interact with us to achieve effect of execute attribute command. Then we found the following application: terminal application or script language interrupter. We found that there is such app that can execute the parameter passed by deep link as a command, like this. We get a reverse shell by download and run BusyBox as netcat by start terminal with this deep link. In order to start app with deep link, we need a more powerful privileged application interface, and we found an interface like this. Browser.start activity with deep link. Compared with interface open app, this method can pass the parameter and more flexible. We can use it to launch terminal app and transfer data to reverse shell. Let's watch a video. Finally, a case about WebView-based Android app. Most of all Android app-based WebView can be launched from browser. But there are also some differences. The browser can load the content of any website, but a web-based app can generally display some vendor-related content. When the app receives some untrusted content, it may even jump out to browser to open it. The case is default App Store or mobile phone. The target app is a vendor's built-in App Store application, similar to the Google Play application. Apps can be installed and opened silent from target app. And the target app can be launched from browser, which means browsable. In summary, the target application is a good target for point-to-all or Tianfu Cup. Let's look at the first activity we found. It is export browsable and register for rich deep link. It handles intent and distribute to different web-based activities. The code is like this. Activity 1 divide links to following three types. Untrusted website, it will jump to browser to open it. And vendor-related site, it will open in activity with web view with no privilege application interface. And finally, website related to App Store business, it will open in activity or website or web view with privileged application interface. And then activity 2 we care. It is an activity or web view with privileged application interface, but no way to load to untrusted domain. The code is like this. And then we analyze the useful privileged application interface. One is the market.openApp. Apps can be opened based on the app name string. Another is the market.installApp. App can be opened based on the app name string. And a callback for install app can be set. We can use this callback to open app after install. But we didn't find a way to load our own website in activity 2. We have to find a way to load our HRP first. After some research, we found a target, activity 3. This is an activity with web view with no privileged application interface, but vulnerability can inject attribute page content like this. What we have now, first is activity 1. It receives the intent set by browser and start activity 1 or activity 2. And activity 2 have privileged application interface to open and install app. And activity 3 can load arbitrary website. Is it possible to attack web view in activity 2 through web view in activity 3? After our test, web view between different apps have complete site isolation, but there is only one web view render process in the same app. That means there is no site isolation between different web view in an app. So we complete the attack. That is browser to activity 1, then to activity 2, then return to activity 1, finally jump to activity 3, and achieve sandbox escape. Let's watch a video. That's all demos. There are our suggestions for app developers. First, make subtle isolation configurable to protect a privileged domain. Then perform same arrange judgment first and then decide whether to reuse the process. And restrict privilege on JavaScript interface to prevent excuse privilege. And use immutable code whenever possible to implement a high-risk operation. And finally, timely fix supply chain vulnerability introduced by Chrome. And there is a acknowledgement. I would like to express our gratitude to the following people we have been helpful to the topic. Thank you for hearing.